Hello everyone, welcome back to MP Coding. Today, I am going to show you how to configure the SDRAM with STM32 correctly. For that, I am going to use the STM32F429 DISCO board. It comes with 64-bit SDRAM. I am going to start with the scratch, how to configure it with STM32. Not going to use the default configurations that I generated from the STM32Cube IDE. Let's get started. First, I've opened the Discovery board's datasheet. For this example, we're focusing only on the SDRAM section. I've also opened the board schematic so we can see exactly how the SDRAM is connected to the microcontroller. By looking at the schematic, we can check the SDRAM pin configuration. This helps us understand how it's physically wired to the MCU. Most SDRAM chips use a similar setup, so once we understand how the SDRAM is configured on this Discovery board, we can apply the same knowledge elsewhere. We are using DISCO board. We don't need to do any extra soldering or custom PCB work just to test this SDRAM. This particular board uses this SDRAM chip from ISSI, and I've also opened its datasheet. It has speed grade of 7. Later we need these settings. If we look at the internal structure of the chip, we'll see it uses address lines A0 to A11, which gives us 12 address bits. It also has data lines DQ0 to DQ15, so it supports 16-bit data. The chip contains 12 row address latches and 8 column address latches. Operates at 3.3 volts, and is organized internally as a 4-bank SDRAM with a synchronous interface. This information is important when configuring the SDRAM in our STM32 code. I recommend reading the datasheet carefully if you want a deeper understanding of how this chip works. Now, let's jump into the example and start writing the configuration step by step. Open STM32Cube IDE and start a new STM32 project. In the board selector, choose the STM32F429 Discovery board. Once selected, click Next, give your project a name, and click Finish. Cube IDE will initialize all peripherals with their default settings. For now, we'll take a quick look at those defaults, but we won't be using them. We're going to start completely from scratch. You'll see the default pinout configuration. If you look closely, you'll notice that many pins are already assigned with different functions. Let's focus on the FMC interface. You'll see that the SDRAM pins and settings are already pre-configured for the onboard SDRAM. This is useful as a reference, but to build our understanding, we'll clear everything and set it up ourselves. To clear all pins, open the Pinout drop-down menu and select Clear Pinouts, then click Yes to confirm. Now, you'll see that all the pins have been cleared. Let's start with the clock configuration. The STM32F429 Discovery board uses an 8 MHz external crystal oscillator. Open the RCC settings and set the high-speed clock to crystal ceramic resonator. This will automatically configure PH0 and PH1 as the RCC input and output pins. Next, go to the Clock Configuration tab. Set the external oscillator frequency to 8 MHz. Then, configure the system to use the maximum HCLK frequency of 180 MHz. After that, go to the System Configuration section, and make sure Serial Wire Debug is selected. This board has an ST-Link programmer built in, so we'll need SWD enabled. Finally, let's enable 2 onboard LEDs to verify our setup later. On this board, LED1 and LED2 are connected to PG14 and PG13. Set both of these pins to GPIO output mode. Now let's configure the SDRAM. First, open the FMC configuration. To understand how the SDRAM is connected, let's take a quick look at the board schematic. On this board, the SDRAM uses SDCKE1 for the clock enable and SDNE1 for the chip enable. These are the control pins that connect the SDRAM to the MCU. Select these pins in Cube IDE. If you're using a custom PCB, you can choose either 0 or 1, depending on your layout. But before changing anything, make sure to consult the datasheet, since these control pins are sometimes fixed and can't be remapped easily. For the Discovery board, we'll stick to the default configuration. These pins are already correctly connected. The SDRAM on this board has 4 internal banks, so select 4 banks in the configuration. Next, for addressing, this SDRAM uses 12 address bits, which gives us access to 4096 rows. Even though the STM32 can support up to 13 address bits, we only need 12 here. Now for the data bus, the SDRAM provides 16 data lines, from DQ0 to DQ15, so we'll use the full 16-bit data width. To enable full 16-bit access, we also need to activate both low and high data mask pins, DQML and DQMH. Enabling both ensures the MCU can access the full 16-bit bus without restrictions. NBL0 and NBL1, these pins correspond to the low and high byte masks. You'll see that these pins are automatically configured when you select 16-bit mode in the FMC settings. Next, we configure the control and timing parameters. This SDRAM is connected to FMC Bank 2, so make sure Bank 2 is selected. The SDRAM uses 8 column address bits and 12 row address bits, so set those accordingly in the configuration. Now let's set the cache latency. But before that, we need to decide on the SDRAM clock speed. Earlier, we set HCLK to 180 MHz. If we set the SDRAM clock to 2 HCLK cycles, that gives us a 90 MHz SDRAM clock. To help with timing calculations, I've created a small cheat sheet with all the key values taken from the datasheet. According to the SDRAM, the speed grade is 7, which means it supports up to 143 MHz at cache latency 3, and up to 133 MHz at cache latency 2. Since we're using a 90 MHz SDRAM clock, both options are valid, but I'll go with cache latency 3 for better stability. Next, set write protection to disabled. Enable burst read, and set the read pipe delay to 1 clock cycle. Now let's go through the timing configuration. This part can seem confusing, so I'll break it down using the cheat sheet. Based on the datasheet, low to active delay is 2 clock cycles. Set it to 2. You can read the ST community post. I used that to calculate these timing parameters. Next up, exit self-refresh delay. It's calculated using this equation. The rest of the timing values I will quickly fill in. You can use my cheat sheet or the ST-Link community post to calculate these. Now let's check the pinout. The default pin configuration matches the schematic, and the Discovery board already uses these pins. If you want to double check, compare the schematic with the assigned pins in CubeIDE. Once everything is set, go ahead and generate code. First, close the .ioc file. Now, let's look at the generated code. If you open the FMC initialization section, you'll see that STM32 CubeIDE has generated some basic configuration based on what we selected earlier. This sets up the FMC peripheral. However, that alone isn't enough to fully initialize the SDRAM. We'll need to add some additional code manually. I've already prepared this extra code in my cheat sheet. It's also available on the ST community forum. I'll copy it from my own sheet for this video. This extra FMC initialization sequence is required to bring up the SDRAM after the controller is configured. The most important part here is programming the external memory mode register, which can look a bit confusing at first. In the SDRAM datasheet, you'll find a mode register definition section. This tells us how to configure various operational parameters for the memory. I've highlighted the values I'm using, but feel free to refer to the datasheet for more detail. After the mode register, we also need to set the refresh rate. According to the datasheet, the SDRAM refresh all 4096 rows within every 64 millisecond cycle. Using the formula provided, and assuming a 90 MHz SDRAM clock, the calculated refresh count comes out to around 1386, or 0x56A in hex. After MX FMC init, add the new FMC init function. That completes the SDRAM hardware initialization. Before we test the SDRAM, let's make sure the project builds and runs by toggling the onboard LEDs. Build a project. If everything compiles successfully, debug and run it. If the LED blinks, we know the system is up and running. Now let's test the SDRAM by writing some data to it. In my cheat sheet, I've included several test functions for writing to SDRAM. But first, let's define the SDRAM memory region. I've found the relevant reference manual for this MCU. 。 . 。 . 。. 。. 。. 。. 。. 。. 。. 。. 。. 。. 。. 。. 。. 。. 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 .
。 . 。 . . . 。 . 。 .
5. And if you go to under FMC and external device address mapping, we can see we have the FMC memory banks as well as addresses for the relevant memory map. We are using SDRAM bank 2, and on the we can see that the start address of this SDRAM bank 1 is at 0xd followed by 7 zeros. And extends all the way to 0xd followed by 7fs in HEX. So we get 4 times 64 megabytes of course. We're not using all of that for our device, but in theory you could address that much memory. Since our SDRAM is 64 megabits, that's exactly 8 megabytes, so we'll define it in hex. Others are memory size in words and D words. These macros will help us write test functions in byte, word, and double word formats. The clear function writes 0 to the entire memory using 16-bit accesses. You could also do this with memset, but remember, memset only works with byte-level writes and doesn't support setting 16-bit or 32-bit values directly. You could also do this with memset, but remember, memset only works with byte-level writes and doesn't support setting 16-bit or 32-bit values directly. Let's quickly copy other functions also. The write increment bytes function writes incrementing by byte values across the entire SDRAM. Using uint8 type pointer. Words uses 16-bit values. With uint16 pointer. dwords uses 32-bit values. With uint32 pointer. Let's copy this FMC test function. It runs each of these tests in sequence and measures how long each one takes using howGetTick. Add this FMC test function after FMC initialization. Add breakpoints after each function to measure how long each one takes to execute. Build the project again, then debug the code. Before resuming execution, go to the Memory tab in Cube IDE. Click the plus icon, and enter the SDRAM start address. You can also add the ending address to observe the full memory space. Now click Continue. The first breakpoint hits after clearing the SDRAM. If you look at the memory view, you'll see all values set to 0, confirming the clear operation worked. Hover over FMC test stop, and you'll see it took about 466 milliseconds to clear all 8 megabytes. Click Resume again. This time, it writes incrementing byte values. You'll see the SDRAM memory fill up in sequence. The byte write took around 10-25 milliseconds. Resume again. This runs the word write. It performs 16-bit writes. It completed in about 536 milliseconds, nearly twice as fast as the byte write. Resume one more time. Now it performs 32-bit writes. You'll see the data increment in 32-bit chunks. And this took only 256 milliseconds, the fastest compared to others. even though 32-bit is fastest. I recommend using 16-bit word writes. Since the SDRAM bus is 16-bit wide, this provides a good balance between speed and reliability. And that's everything for this tutorial. I hope this walkthrough helped you understand how to configure SDRAM correctly with STM32 using the STM32F429 Discovery board. All the example code, cheat sheets, and reference documents I used will be available on my GitHub. Check the link in the video description. In the next video, I'll show you how to integrate SDRAM with a TFT display using the same Discovery board, so stay tuned.